Hello friends, how are you? This is again the revision time for hydraulics and pneumatics classes. Today we'll take the third chapter, that is flow through pipes. This chapter carries 15 marks. In this chapter we are discussing about when the fluid flows through the pipes, what are the different losses that can occur in the pipe due to the flow of the fluid. You can expect one problem from this chapter mainly on the two formulae. One is Chase's formula, second one is Darcy's formula. And also you can expect one 5 marks question. Usually it is on the losses in the pipes or explain the Darcy's formula or explain the Chase's formula or some other theories which I am going to revise in this class. So in this chapter, the main thing I would like to revise is regarding the introduction, that is flow through pipes. Then what are the different losses? They are usually called as head losses through the pipe, and the classification of these losses means the major losses as well as the minor losses. Then we'll discuss again about the HGL, that is hydraulic gradient line, and also total energy line, that is TEL, and also regarding the power transmission through the pipe and flow through the nozzle at the end of the pipe, and at last we want to discuss about the water hammer in the pipe. So all you know, the very common or familiar word is pipe. How we define the pipe? A pipe is a cylindrical body through which the fluid is flowing. Actually, pipe is a passage with a closed perimeter through which the fluid flows under pressure. Fluid is flowing through the cylindrical object called as a pipe. The fluid flowing in the pipe is always subjected to resistance due to shear forces between the fluid particles and surface of the pipe. You know that when the two parts which are moving with each other are in contact with each other, then there is a resistance, and here the resistance is due to the shear forces between the fluid particles and the surface of the pipe, and this resistance is known as a frictional resistance. The losses through the pipe. The losses through the pipe depends upon the type of the flow. We already discussed the different types of flow in the previous chapter. The two types of flow which are responsible for the head losses through the pipe are: one is a laminar flow, second one is a turbulent flow. You already know that in a laminar flow the fluid travels smoothly as shown in the figure in regular paths, or you can say that the streamline. You know that streamline is the representation of the fluid flow, graphical representation of the fluid flow. The streamlines are parallel to each other in laminar flow, whereas in a turbulent flow the fluid undergoes irregular fluctuations and mixings. You can see the figure where we can see the streamlines are moving randomly and irregularly, and this kind of flow is called as a turbulent flow. Then how we are going to classify the losses in the pipe? We already studied that when the fluid flows through the pipe, there are some losses because of the resistance between the fluid as well as the pipe surface. And these losses are mainly classified into two categories. One is a major loss, second one is a minor loss. Major loss is mainly the friction loss. It is due to the friction between the fluid and the pipe surface. Whereas minor loss is again classified as the loss due to the sudden enlargement, the loss due to the sudden contraction, the loss at the entrance of the pipe, the loss at the exit of the pipe, and the loss due to the pipe fittings. So this question usually carries a 5 marks. What are the different losses? You can write major loss, minor loss. Major loss is a frictional loss. Minor loss is again classified as the sudden enlargement loss, sudden contraction loss, the loss at the entrance of the pipe, the loss at the exit of the pipe, and the loss due to the pipe fitting. Here we'll take one by one in detail. The major loss. It is the loss of head due to the friction, and it depends on the velocity of flow and also the diameter of pipe and the roughness of the pipe. And it is denoted as HF, and it is given as HF is equal to FL V square divided by 2GD. The friction loss is given by FL V square divided by 2GD. And the minor losses. So minor loss, the first one is the loss at the loss due to sudden enlargement. Means in this figure you can see the fluid is flowing from narrow diameter to the larger diameter. Means suddenly there is a increase in the size of the pipe, and this loss is called as the sudden enlargement loss. It is denoted by HE, H suffix E. Similarly, the loss due to sudden contraction. It is the opposite. Means here the fluid is flowing from larger diameter pipe to a smaller diameter pipe, and where the area of the pipe decreases. Hence, it is called as a loss due to sudden contraction. It is denoted as HC, and it is given by HC is equal to 1 by CC minus 1 bracket square into V square by 2G, where Cc is called as coefficient of contraction. The third loss is loss at the exit. You can see the figure. At the end, the pipe water, the fluid is flowing from the end of the pipe to the container, and this loss is known as loss at the exit of the pipe, and it is denoted as HX. X means exit. Similarly, the loss due to the pipe fittings. You can see the different pipe fittings. The pipe fittings includes elbows, valves, T's, etc. And it is denoted as HB. It is given by K into bracket V square by 2G. And the loss at the entrance. So means when the fluid enters the pipe, there is a loss which is represented as HEN. It is given by HEN is equal to 0.5 into bracket V square by 2G. Now I want to explain one more important question which is about the representation of two types of lines. They are called as HGL, that is hydraulic gradient line, and TEL, that is called as total energy line. So means if the fluid is flowing through the pipe, we can take the center of the pipe as a datum point, or it is the center line. The hydraulic gradient line, that is HGL, is the sum of the pressure head and datum head. Means pressure head is P by rho and datum head is Z. Therefore, HGL is P by rho plus Z. If the datum line coincides with the center line, then Z is equal to 0. Then HGL is equal to only P by rho, that is represented on the pipe. You can see in the figure. So it is also defined as the line joining all the liquid levels in piezometers. It is the line joining all the liquid levels in piezometers. The slope of HGL is also known as hydraulic gradient. In a total energy line, that is TEL, it is a graphical representation of total head. Total head means sum of pressure head, velocity head and datum head. Pressure head is P by rho, velocity head is V square by 2G and datum head is Z. Therefore, TEL is equal to P by rho plus V square by 2G plus Z. If the datum line coincides with the center line, then Z is equal to 0. Then we will be having only two heads, that is pressure head and velocity head. So this is again an important question for 5 marks. Now, how do you find the loss of head due to the friction? to find the loss of head or energy due to the friction, we are using two main formula or two main equations. One is called as Darcy-Weisbach equation, which is popularly known as Darcy's formula, Darcy's equation. It is given by HF is equal to 4FL V square divided by 2GD. I'll repeat, HF is equal to 4FL V square divided by 2GD, where HF is the loss of head due to friction. F is coefficient of friction, and this value usually given in the problem. Otherwise, it is calculated as F is equal to 16 divided by RE, where RE is the Reynolds number and RE less than 2000 is for RE for viscous flow. We can take it as a value is less than 2000 value. V is the mean velocity, D is the diameter of the pipe, and L is the length of the pipe. Another important equation is Chase's formula or Chase's equation. It is used to find the velocity of fluid in the pipe. It is given by phi is equal to C into root of mi, where m is equal to d by 4. D is the diameter of the pipe. I is equal to hf by L. Hf is the loss of head due to friction and L is the length of the pipe. And C is the Chase's constant, which will be given in the problem. When the fluid flows through the pipe, the power is transmitted through the pipe. And if you want to calculate what is the maximum amount of power that is transmitted through the pipe, it is given by HF is equal to H by 3, capital H by 3, where HF represents loss of head due to friction and capital H is the total head. Therefore, the 1/3 of the total head is the maximum power transmitted. The condition for maximum power transmission is HF is equal to capital H by 3. And if you want to calculate the efficiency for the power transmission, which is given by the ratio of the power available at the outlet of the pipe to the power available at the inlet of the pipe. So power available at the outlet of the pipe is difference between the total head and the frictional head, that is H minus HF, and power available at the inlet is capital H. Therefore, efficiency is given by capital H minus HF divided by capital H. And the maximum efficiency will be, if you substitute HF is equal to H by 3, and we can find that, we can calculate that the maximum power is about 66.67%. So this power transmission through the pipe can also be derived. The power is transmitted by the liquid which is flowing through the pipe, and it is commonly used to convey water from a high level reservoir to turbine house and in operation of hydraulic equipments like hydraulic press, crane jack, etc. The power transmitted depends upon the weight of the liquid flowing through the pipe and the total head available at the end of the pipe. Therefore, the power transmitted through the pipe P is equal to weight of water flow through the pipe into head available at outlet of the pipe. Weight of water we call it as W, and head available is the difference between total head and the frictional head, that is capital H minus HF. But W is equal to M into G, where M is called as mass of the fluid, mass of the water you can say. But mass is also given by density into area into velocity of water. Therefore, rho into A into V into G into bracket H minus HF. This is therefore power transmitted is given by rho into G. Area of the pipe is pi by 4 d square into velocity V into bracket H, that is total head, minus the frictional loss is 4FL V square divided by 2GD into W. This is W means it is watt. Unit of power is watt. So here I am showing that figure that reservoir is connected to the turbine by means of a pipeline. Through the pipeline, the water is flowing, and the power, how much power is transmitted through this, we are calculated by using that equation. And at the end of the pipe, usually we are connecting a nozzle. And the function of the nozzle is to convert the total energy of liquid into kinetic energy. Nozzle is used where higher velocity of liquid is required, especially in case of a Pelton wheel, or in case of a firefighting, or in case of mining power developments, etc. As water is flowing continuously through the pipe as well the nozzle, we can apply the law of continuity. That is, Q is equal to capital A into capital V is equal to small a into small v. Capital A represents capital V represents the pipe. Small v represents the nozzle. The head at the inlet of nozzle is H minus HF. Here we are neglecting the minor losses. Head at the outlet of the nozzle is kinetic head only, that is V square by 2G. Hence, according to the Bernoulli's equation, head at inlet is equal to the head at exit. That is, capital H minus HF is equal to V square by 2G. Substituting the value of HF, that is 4FL V square by 2GD, we get H minus 4FL V square by 2GD is equal to V square by 2G. But we know that capital V is equal to small a by capital A into V. Substitute this value. In case of V, we get V is equal to 2GH under root of 2GH divided by 1 plus 4FL A square, small a square by capital A square divided by D. Therefore, discharge through the nozzle is A into V. Therefore, Q is equal to A into under root of 2GH divided by 1 plus 4FL A square divided by D into A square. And note that the condition for transmission of power through the nozzle is the same to that of the pipe. Means here also HF is equal to H by 3. One more important term while discussing the fluid flow through the pipe is water hammering. Here actually two things. One is water hammering, second one is called as knocking. Usually we observe in case of water flowing through the pipe. When the water is flowing through the pipe, it possesses momentum due to the velocity of water. But if this flow is suddenly brought to rest, usually by closing the valve, then the momentum of the water is destroyed. This causes a high pressure waves, and these high pressure waves will be transmitted along the length of the pipe with a velocity equal to the velocity of the sound wave. Hence, it produces a noise, and this noise is called knocking. Means when the water is flowing through the pipe, if suddenly the valve is closed, because of the destruction of the momentum of water, very high pressure waves are created in the pipe, which will travel along the length of the pipe equal to the velocity of sound wave, and hence it produces a noise, and that noise is called as knocking. If this wave of high pressure has the effect of hammering action on the walls of the pipe also, and hence it is called as water hammer. When the pressure is, if it is more velocity, then what happens, it will cause a hammering effect on the pipe sides. Hence it is also known as a water hammering. There are three different cases of water hammering depending upon the time taken in closing the valve and type of the pipe also. The first case is water hammer when valve is closed. And the second one is water hammer when the valve is closed suddenly and the pipe is rigid. Third case is water hammer when the valve is closed suddenly but the pipe is elastic. This figure gives you the idea regarding the water hammer. In the first figure, valve is closed, the water present in the pipe is stationary, still it is stagnant, it is not flowing. When the valve is opened, the water flows through the pipe. If now the valve is closed suddenly, then you can see the zigzag, that is nothing but a pressure waves, a very high pressure waves are developed, and that will produce a sound, that is knocking, and also produce a water hammer. This figure gives you the formation of the water hammering. So this is about a theoretical part of this chapter, and as I told you, there are some problems to be solved in this chapter. Usually 7 to 8 marks problems will be getting, and that problems we'll discuss in the next video. Until then, goodbye. Thank you.